Today we're going to do a little review on exponents. So, let's talk about exponents a little bit. We do know that in exponents, we have to have a base raised to an exponent that'll give us an answer. For example, 8 squared is 64 because 8 times 8 is 64. We also know that there's some properties out there of exponents. One property is what's called power to a power. So if I had x to the second raised to the third, it would become x to the sixth because you multiply the exponents when it's power to a power. When you have common bases and you're multiplying with exponents, so let's say x to the second, y to the third, times x to the fourth, y to the sixth, you add the exponents. So you would have x to the sixth, y to the ninth. When you have common bases and you're dividing with exponents, let's say x to the fourth, y to the fifth, divided by x to the third, y to the eighth. You subtract the exponents, you would end up with x to the first, or just x, and y to the negative third. The only problem here is that you can't have a negative exponent, so that would be rewritten as x over y cubed. By placing the base who has the negative exponent in the denominator, the exponent then becomes positive. Okay, and a couple other things to know about would be that you can take a radical and rewrite it as an exponent. For example, the fifth root of x to the 10th can be written as x to the 10 fifths, where my root is my denominator, my exponent is my numerator, which can be simplified then to x squared. It's just another way of writing an actual root. You can do it as an exponent. Another thing you need to know about exponents is the graphs of exponential equation. Every exponential equation can be graphed. Let me set up a little graph here. Here's my x-axis, my y-axis. Every exponential equation goes through point 0, 1. We'll stay in quadrants 1 and 2, and we'll never touch the x-axis. So, again, we'll go through quadrants 1 and quadrant 2. We'll pass through point 0, 1, and the x-axis will become that graph's asymptote, which is a line that graph will get as close to it as it possibly can, but will never touch it. These rules go for every exponential equation. So any exponential equation you graph, either in your calculator or by hand, will always be in quadrants 1 and 2 and pass through point 0, 1, and will get as close to the x-axis as possible, but will never touch it. So those are just some preliminary things about exponents. Let's now go into a couple things about equations. So there's two types of exponential equations. One type of exponential equation is when you have an exponent on only one side of the equation. For example, if I had x raised to the 2/3 power minus 1 equals 24, I need to isolate the base and the exponent in order to get rid of the exponent. So to do that, in this case, I'm going to need to add 1 to both sides, and I'll get x to the 2/3 power equals 25. Now, in order to undo that exponent, I can raise it to its reciprocal power, because in doing so, we just reviewed the rule of power to a power where you multiply the exponents. I would end up with 6, 6, which is 1, and anything to the first power is itself, so basically I'd have plain old x on the left. But the rule in equations is whatever you do to one side, you have to do to the other. So you'd have to raise 25 to the 3/2 power, and you'd end up with 125. Let's do another one like that. If I had 2x raised to the negative 1/3 power equals 6, again, I need to isolate the base and the exponent, so in this case I'm going to divide each side by 2 and get x to the negative 1/3 equals 3. I'm going to raise each side to the negative reciprocal, or the reciprocal of negative 1/3, which is a negative 3 over 1, or plain old negative 3. Because of the original is a negative, its reciprocal is a negative. And I end up with x equals 1 over 27. So there's just a little review on how to undo an exponent when you only have one in an equation. Well, what happens if you have exponents on both sides of your equation? Well, in that case, you're going to want to look for common bases. So, for example, if I had 4 to the x equals 4 to the 2x plus 1, if I have common bases, I can drop the bases and set the exponents equal to each other and solve. So in this case, I'm going to subtract 2x on both sides and get a negative x equals 1. Divide each side by a negative 1. X is a negative 1. Well, what happens if I don't have common bases? So if I had, let's say, for example, 4 raised to the 3x equals 8 raised to the x plus 1, I'd have to find a common base. Well, the rule in doing this is you either use the smaller of the two bases or you go smaller. So the smaller of the two bases is 4. 4 raised to any power will give me 8. No, 4 raised to the second, or 4 squared, is 16, so I can't use the 4. So I have to go smaller than 4, and I'm going to use 2. 2 squared is 8, and 2 cubed, let's try that again. 2 squared is 4, and 2 cubed is 8. All I'm doing right now is rewriting the bases of 4 and 8. Those are still being raised to the original exponents. So now I've got power to a power rule. So now I have 2 to the 6x equals 2 to the 3x plus 3, because when you multiply one thing by many, it's distributive property. Now I've got common bases. At this point, I can drop the bases, set the exponents equal to each other, and solve. I'll subtract 3x on both sides. 3x equals 3. I'll divide each side by 3. X is 1. So basically, I just went over a quick review on exponents, on how to actually solve using common bases, solve when you're raising each side of the equation to the reciprocal exponent. We went over the properties and what an exponential curve looks like. Hopefully this will help you. Again, please feel free to review this video at any time.